The story of Pythagoras and the origin of his famous theorem begins not merely with numbers or shapes, but with a search for truth that goes beyond measurement. Pythagoras of Samos, who lived around the 6th century BCE, was more than a mathematician. He was a philosopher, a mystic, and a visionary who sought to understand the hidden harmony of the universe. The world in which he lived was still young in its understanding of science. People measured land, built temples, and observed the stars, but few saw in those patterns a unifying law that could explain both nature and thought. Pythagoras changed that by proposing something radical, that everything in existence could be understood through numbers, and that numbers were not just symbols but living principles shaping the cosmos itself. Before Pythagoras, ancient civilizations such as the Babylonians and Egyptians had already discovered numerical relationships similar to what we now call the Pythagorean theorem. Babylonian tablets dating more than 1,000 years before Pythagoras show calculations that satisfy the relationship between the sides of a right-angled triangle. Egyptian surveyors used a 3-4-5 triangle to measure land boundaries along the Nile, ensuring perfect right angles in their architectural designs. Yet, while these cultures used the concept practically, they did not explore its deeper nature. They treated it as a tool rather than as a universal truth. Pythagoras and his school transformed it from a craft into a philosophy, turning geometry into a way to uncover the divine structure of existence. When Pythagoras established his school in Croton, southern Italy, he created more than a center of learning. It was a community that viewed mathematics as sacred knowledge. His followers, known as Pythagoreans, lived by strict rules of discipline, silence, and harmony. They believed that by studying mathematics, one could purify the soul and draw closer to the divine. Among their most cherished discoveries was the relationship between the sides of a right triangle. For them, this was not merely a property of shapes. It was a reflection of universal balance. The triangle became a symbol of perfection, representing the harmony between different forces, the finite and infinite, the tangible and the abstract, the human and the divine. The theorem itself states that in a right-angled triangle, the square of the hypotenuse equals the sum of the squares of the other two sides. Though simple in expression, this relationship opened a window into the structure of space and logic. It revealed that even something as physical as distance could be expressed in terms of pure thought. Geometry, once seen as a branch of craftsmanship, became a way to reason about invisible truths. Pythagoras's insight bridged the physical and the metaphysical, demonstrating that the same harmony governing sound and music could also describe form and space. For the Pythagoreans, the significance of this discovery reached into every part of life. They believed that the world was built upon numerical ratios, that everything from the motion of planets to the resonance of a lyre followed the same fundamental order. When they looked at the right triangle, they saw not a static shape, but a dynamic symbol of balance, a union of opposites held together by a perfect law. This idea of harmony became a cornerstone of Western thought. It influenced not only mathematics, but also philosophy, architecture, and art. The idea that beauty and truth arise from proportion can be traced back to the Pythagorean vision. Yet, much about Pythagoras himself remains shrouded in mystery. He wrote no books that have survived, and much of what we know comes from later philosophers like Plato and Aristotle, who were deeply inspired by his ideas. Some stories about him border on legend, that he could hear the music of the spheres, that he remembered his past lives, or that he discovered mathematical truths through divine revelation. Whether these stories are fact or myth, they capture how profoundly his ideas affected those who followed him. To his disciples, he was not just a thinker but a kind of prophet whose teachings revealed the underlying unity of all things. The origin of his theorem, therefore, cannot be separated from the spiritual and philosophical movement that surrounded it. The discovery was not made in isolation, but as part of a larger quest to understand the essence of existence through reason and symbolism. The theorem became a key that unlocked the relationship between the tangible world and the abstract order that governed it. To prove that a perfect relationship existed between the sides of a triangle was to show that order itself could be discovered through thought, and that mathematics was the language of that order. The influence of this idea extended far beyond ancient Greece. The theorem became a foundation upon which later thinkers built the entire edifice of geometry. Euclid, in his Elements, would formalize it as Proposition 47, giving it a logical proof that could be universally applied. But the spirit of the discovery, the idea that reason could reveal eternal truth, remained Pythagorean at its core. Every geometric proof and every algebraic formula that followed carried within it the same belief that reality is intelligible, that beneath the surface of nature lies a pattern waiting to be uncovered. In many ways, the Pythagorean theorem represents the birth of abstract reasoning. It showed that truth could exist independently of physical evidence, that through logic alone, the mind could reach conclusions that applied to all possible triangles, everywhere and forever. This was an extraordinary leap for humanity. It marked the beginning of mathematics as a universal language, a language through which the human mind could communicate with the cosmos. The theorem thus became not just a mathematical law, but a symbol of human curiosity and the power of intellect. The mystery surrounding Pythagoras adds to the allure of his theorem. Was he the true discoverer, or did he inherit it from older civilizations? Did he see the relationship as a mathematical rule or as a divine revelation? History may never give clear answers, but perhaps that uncertainty is part of the beauty. Pythagoras's legacy is not confined to proof or calculation. It lies in the vision that knowledge, when pursued with reverence and reason, can uncover the hidden harmony that connects all things. Right-angled triangle stands as one of the simplest yet most profound shapes in mathematics. At first glance, it appears ordinary, a figure made up of 3 straight lines meeting at 3 points. Yet within this modest structure lies a deep and timeless pattern that connects the world of form, space, and logic. The Pythagorean theorem brought this figure into the center of mathematical thought, transforming it from a simple geometric object into a symbol of universal balance. The triangle's right angle, where 2 sides meet in perfect perpendicularity, represents precision and order. It embodies the human desire to measure, to define, and to find clarity in the complexity of the world. The structure of the right-angled triangle is not only mathematical but philosophical, reflecting the harmony between unity and duality, between the finite and the infinite. Every right-angled triangle tells a story about relationships. Its sides are bound together in perfect proportion. The hypotenuse, which stretches across the triangle's longest distance, is always in precise relation to the 2 shorter sides. This relationship, expressed through the equation a2 plus b2 equals c2, a2 plus b2 equals c2, a2 plus b2 equals c2, is more than a rule. It is a statement about how balance manifests in both nature and thought. When the 2 smaller sides represent separate directions or dimensions, the hypotenuse represents their union. It shows how combining 2 independent movements, horizontal and vertical, creates something new and complete. The triangle becomes a metaphor for synthesis, for how opposing forces can coexist in equilibrium. The structure of the right-angled triangle fascinated mathematicians because it revealed that geometry could express absolute truth. Regardless of the triangle's size, whether drawn in sand or carved in stone, the relationship between its sides never changes. It is a law that transcends material boundaries, existing purely in the realm of thought. This consistency offered ancient thinkers proof that reason could reveal eternal truths. They saw in the triangle a model for understanding the cosmos stable, symmetrical, and governed by order. The triangle's exactness mirrored the order they believed existed in the heavens, where stars and planets moved according to invisible but precise principles. The right angle itself carries deep symbolic meaning. In architecture, it defines the stability of walls, floors, and foundations. In art, it provides perspective and proportion. In philosophy, it signifies integrity and uprightness, the alignment between truth and action. When the ancient Egyptians used ropes knotted in ratios like 3, 4, 5 to construct their pyramids, they were not merely building with accuracy, they were invoking a sense of cosmic harmony. The right-angled triangle ensured that human creation reflected natural order. Its use in temples, monuments, and sacred spaces across civilizations reveals how geometry became intertwined with spirituality. The mathematical beauty of the right-angled triangle also lies in its ability to connect geometry and algebra. By squaring the sides and comparing their areas, the Pythagorean theorem bridges the visual and the numerical, turning shapes into equations and equations into shapes. This blending of abstract reasoning with visual intuition was revolutionary. It allowed the human mind to move freely between two worlds, the world of form and the world of number. The triangle thus became the meeting point between thought and reality, where the invisible could be made visible through precise relationships. Its structure also inspired exploration beyond flat geometry. When mathematicians extended the idea of right angles into 3 dimensions, they discovered new relationships governing cubes, spheres, and higher shapes. The concept of perpendicularity evolved into a cornerstone of space measurement, leading eventually to vector analysis and the geometry of space-time. Even in these modern developments, the simple right-angled triangle remains at the heart of the reasoning. Every coordinate system, every physical law describing direction and force, is rooted in the logic of the right angle. The triangle became not just a shape, but the foundation of how space itself is understood. The right-angled triangle also represents the beginning of proof-based reasoning. Ancient builders may have known how to create right angles practically, but it was the Greeks who sought to understand why such relationships held true. The structure of the triangle encouraged the development of deductive logic, where truth is derived step by step from known principles. The Pythagorean theorem became a perfect example of how reason could turn observation into certainty. It inspired Euclid to build his entire system of geometry on logical proof, creating a method that would guide scientific thinking for millennia. The right triangle, in this sense, became a teacher of reason itself. In the natural world, the structure of the right-angled triangle appears in countless forms. The slope of a mountain, the path of light across water, the flight of a bird forming a diagonal across the sky, all follow geometric patterns that can be analyzed through right triangles. Engineers use it to design machines, bridges, and buildings. Physicists use it to describe motion and force. Even in digital spaces, computer graphics rely on calculating pixel distances through right triangle relationships. The simple formula linking sides and diagonals underlies technologies that define modern life. The triangle's timelessness lies in its universality. It describes patterns found in both ancient architecture and virtual reality. But beyond its practical uses, the right-angled triangle continues to evoke wonder because it expresses an ideal of balance. Two sides, standing at right angles, represent distinction and independence, yet their union through the hypotenuse represents connection. It is a visual and mathematical symbol of harmony, how separate forces can combine without losing their identity. The triangle embodies both stability and dynamism. It stands firm, yet its form points outward, suggesting movement and extension. This balance between rest and motion mirrors the human condition, where opposites reason and emotion, matter and spirit, seek equilibrium. The timeless structure of the right-angled triangle reminds humanity that beauty can emerge from simplicity. In its three sides lies a universe of meaning, the power of proportion, the order of logic, and the poetry of balance. The theorem that defines it is not just a rule for measurement, but a revelation of how nature itself organizes relationships. Whether carved in stone, drawn in a notebook, or calculated by a computer, the right-angled triangle continues to represent the elegant intersection of truth, form, and harmony. The relationship between geometry and algebra stands as one of the greatest intellectual bridges in human thought, and the Pythagorean theorem serves as the earliest and most elegant link between the two. Geometry deals with shapes, space, and form, the visual and tangible side of mathematics, while algebra deals with numbers, relationships, and the abstract. The union of these two realms reveals how physical reality can be described through logical symbols, and how numbers themselves can carry meaning beyond quantity. The Pythagorean theorem, expressed as a2 plus b2 equals c2, a2 plus b2 equals c2, a2 plus b2 equals c2, captures this harmony perfectly. It takes the visual form of a right-angled triangle and translates it into a precise numerical relationship, showing that mathematics is not only a tool for calculation, but also a universal language capable of connecting the seen and the unseen. When we examine the theorem closely, it becomes clear that it does more than compare lengths. It unites two worlds. The idea that the sum of the areas of two squares on the shorter sides equals the area of the square on the hypotenuse is a geometric truth, yet it can be expressed entirely through algebraic symbols. This duality allows the mind to move freely between image and idea, between sight and logic. The Greeks, who valued both reason and beauty, found in this theorem an ideal expression of harmony. It was geometry made rational, and algebra made visible. The power of this union shaped the very foundation of mathematical thought, and continues to influence how we understand patterns in nature, science, and art. In ancient times, geometry was considered the highest form of knowledge because it reflected the perfection of nature. The circle, the square, and the triangle were not just figures, but manifestations of universal order. Algebra, by contrast, emerged as the language of relationships, a way to describe change, proportion, and motion. The Pythagorean theorem revealed that the two were not separate but deeply intertwined. A shape could be expressed as a number, and a number could describe a shape. This realization was revolutionary. It showed that reality itself could be measured, expressed, and predicted through a synthesis of logic and form. Through this connection, the theorem also became the foundation for coordinate geometry, centuries later developed by René Descartes. By merging the visual world of geometry with the analytical power of algebra, Descartes created a system where every point in space could be represented by numerical coordinates. The distance between 2 points, for example, can still be found using the Pythagorean relationship. This innovation changed mathematics forever. It made possible the study of curves, motion, and complex forms in ways that pure geometry could not. From this union arose calculus, physics, and modern engineering fields that define the structure of the modern world. The harmony between geometry and algebra also revealed something profound about the nature of abstraction. The theorem showed that even without measuring a physical triangle, one could reason about all triangles through symbols. This marked a turning point in the evolution of thought. Mathematics became not merely descriptive but creative. It allowed humans to imagine shapes that did not yet exist and to design systems that stretched beyond physical experience. The connection between the geometric and the algebraic thus became a mirror of human imagination itself, the ability to move between vision and concept, between what is and what could be. In practical terms, the blending of geometry and algebra through the Pythagorean theorem opened countless doors of discovery. In architecture, it provided the foundation for symmetry and proportion. In astronomy, it helped calculate distances between celestial bodies. In navigation, it allowed explorers to measure unseen routes and estimate positions using angles and distances. In physics, it underlies the vector relationships that describe motion, energy, and force. Even in modern computer graphics, the distances between points, the shading of surfaces, and the rendering of three-dimensional images depend on the same principle. The theorem's simple relationship has become the silent engine behind many of the world's most advanced technologies. Yet the harmony between geometry and algebra is not merely functional. It also carries a deep philosophical resonance. The Pythagoreans believed that numbers had souls, that each relationship reflected cosmic order. In this sense, the theorem was more than a proof. It was a revelation of balance. The right-angled triangle represented stability and order, and the numerical equality it embodied symbolized fairness and proportion in all things. When geometry and algebra meet, they demonstrate that truth can exist in multiple forms, one visual, one symbolic, and that these forms, though different, speak the same language. The same law that governs a drawn triangle also governs equations in the abstract. This realization affirms that logic and beauty, reason and imagination, are not opposites but partners in discovery. The synthesis also deepened humanity's understanding of mathematical proof. A geometric proof appeals to sight and intuition, while an algebraic proof appeals to logic and manipulation of symbols. When combined, they create a more complete understanding, showing that mathematics is both art and science. One can demonstrate the theorem by rearranging geometric figures, or by substituting algebraic expressions. Both paths lead to the same truth. This duality illustrates how different ways of thinking can converge upon harmony, reinforcing the unity of knowledge. In the broader sense, the connection between geometry and algebra symbolizes the human pursuit of unity in diversity. Just as the sides of the triangle come together in perfect balance, so too do the abstract and the tangible merge within the human quest for understanding. The theorem becomes a metaphor for synthesis in thought, the meeting of logic and perception, of structure and freedom. Every time a student learns to square numbers to find a missing side, they are unknowingly reenacting a discovery that transformed the very nature of reasoning. Through this harmony, mathematics transcends its boundaries. The Pythagorean theorem becomes a timeless conversation between forms and formulas, between the physical triangle and the symbols that represent it. It teaches that truth is not confined to one way of seeing. It can be drawn, spoken, or calculated, and it remains the same. The connection between geometry and algebra is thus more than a mathematical achievement. It is a reflection of how the mind and the world mirror each other, how abstraction gives meaning to reality, and how from the union of shape and number emerges the order that underlies all creation. Behind the Pythagorean theorem lies a depth that transcends mathematics and enters the realm of philosophy. To Pythagoras and his followers, numbers were not simply quantities or symbols used for counting. They were divine principles, forces that governed the structure of the cosmos. The theorem, though geometric in form, represented a universal harmony between matter, spirit, and logic. It showed that beneath the visible world of shapes and measurements lay an invisible order governed by proportion and balance. In the eyes of the ancient philosophers, this was not merely a mathematical discovery, but a revelation of cosmic truth, the realization that the universe itself was built upon numerical relationships, and that to understand these relationships was to glimpse the essence of existence. Pythagoras viewed mathematics as a sacred language capable of expressing the laws of creation. He believed that all things were connected through numbers, and that harmony arose when these numbers related to one another in perfect proportion. This belief extended beyond triangles and into every aspect of life, from music to the motion of the stars. In fact, the Pythagoreans discovered that musical harmony could be expressed through simple numerical ratios. When strings vibrated in lengths related as 2, 1, 3, 2, or 4, 3, they produced pleasing sounds to them. This was proof that the same mathematical relationships that governed geometry also governed beauty and sound. The Pythagorean theorem, therefore, was not isolated in its significance. It was one piece of a grand design where mathematics revealed the hidden structure of reality. The philosophical depth behind the theorem also lies in its symbolic meaning. The right-angled triangle was seen as a representation of balance between opposites. The two shorter sides symbolized dual forces, matter and spirit, finite and infinite, body and mind, while the hypotenuse represented unity, the harmonious resolution of these opposites. The theorem expressed that even contrasting elements could exist in equilibrium through a precise and elegant relationship. In this way, geometry became not just a study of space, but a meditation on existence itself. The balance expressed in the triangle mirrored the moral and spiritual balance that the Pythagoreans sought in life. This belief in harmony extended to the cosmos. Pythagoras proposed that the movements of the planets followed mathematical ratios, creating what he called the music of the spheres. Though inaudible to the human ear, this cosmic symphony symbolized the perfect order of the universe. The same relationships that shaped the right-angled triangle were believed to govern the distance between stars and the rhythm of celestial bodies. For Pythagoras, mathematics was not a human invention, but a divine discovery, the language through which the universe spoke. His theorem was a reflection of this cosmic harmony, a fragment of universal truth expressed in the simplicity of geometry. Philosophically, the theorem also introduced the concept that truth could be reached through reason rather than through sensory perception. Ancient thinkers were beginning to understand that the mind could uncover universal laws that did not depend on observation. The theorem proved that logic and abstraction could yield certainty. No matter what the size or shape of a right triangle, the relationship between its sides remained constant. This realization carried profound implications. It suggested that human reason could access eternal truths that were unchanging, perfect, and beyond the physical world. In this sense, the Pythagorean theorem became a gateway to metaphysical thought, showing that knowledge was not limited to what could be seen, but could be attained through pure intellect. The theorem's philosophical depth also influenced later thinkers such as Plato, who was deeply inspired by Pythagoras. In his philosophy, the material world was seen as an imperfect reflection of ideal mathematical forms. The Pythagorean vision of harmony between number and reality became a cornerstone of Platonic thought, leading to the belief that all truth originates in an unseen world of perfect patterns. This connection between mathematics and metaphysics gave birth to centuries of philosophical exploration. The theorem's simple geometric statement became a symbol for the deeper idea that the universe is logical, structured, and accessible to reason. For the Pythagoreans, this understanding was not merely intellectual. It was moral and spiritual. They believed that to live in harmony with the universe, one must reflect its order and proportion in one's own life. Just as the sides of the triangle existed in perfect balance, so too should the human soul strive for equilibrium between thought, emotion, and action. Mathematics thus became a path to purification, a way to align the self with the divine order of the cosmos. The study of geometry was considered a sacred discipline, capable of leading the mind from the confusion of the material world to the clarity of universal truth. The theorem, simple in form yet profound in meaning, served as a daily reminder that perfection lies in balance and understanding. The philosophical essence of the Pythagorean theorem also lies in its universality. It applies everywhere and always, regardless of context or culture. This timelessness reflects the philosophical idea that truth is eternal. The same relationship that defines a triangle on Earth applies equally to the structure of the stars or the dimensions of an atom. The theorem embodies the principle of unity in diversity, that a single law can govern infinite variations. This idea has influenced not only mathematics, but also art, architecture, and music, where proportion and symmetry are seen as expressions of universal harmony. Even in the modern world, the philosophical legacy of the theorem continues. It reminds humanity that behind the complexity of technology and science lies a foundation of simple, harmonious principles. It encourages the belief that order exists beneath apparent chaos, and that understanding can bring harmony to the unknown. The theorem becomes more than a mathematical statement. It is a symbol of the eternal quest for meaning. Each side of the triangle becomes a path of inquiry, converging toward a truth that is both rational and transcendent. In essence, the Pythagorean theorem represents the moment when mathematics became philosophy, when numbers became symbols of existence, and when geometry revealed the invisible harmony that unites. All things the Pythagorean theorem has long been admired for its simplicity and elegance, yet within its apparent clarity lies a collection of paradoxes that challenge the very idea of simplicity in mathematics. It stands as a formula that every student learns easily, but as mathematicians and philosophers have discovered, beneath that simple expression exists a web of questions that test the limits of human understanding. The paradoxes associated with the theorem emerge when one looks beyond its surface, questioning its assumptions, its universality, and its implications about truth itself. What seems absolute and eternal at first glance becomes, upon deeper thought, a window into the complexity of mathematical reality and the mysteries of human reasoning. One of the earliest paradoxes tied to the Pythagorean theorem is the discovery of irrational numbers. The theorem states that for a right-angled triangle, the square of the hypotenuse equals the sum of the squares of the other two sides. However, when those sides are chosen to have whole number lengths, such as 1 unit each, the hypotenuse becomes the square root of 2. This number cannot be expressed as a fraction or ratio of whole numbers. It is infinite, non-repeating, and unending. To the Pythagoreans, who believed that all of existence could be expressed through whole number ratios, this discovery was catastrophic. It contradicted their deepest belief that the cosmos was built on numerical harmony. The irrational number seemed to represent chaos within order, infinity within the finite. Legend says that the disciple who revealed this truth was cast into the sea, as if the very acknowledgement of irrationality threatened the structure of their philosophy. This paradox shattered the ideal of numerical perfection and opened a doorway to a new understanding that truth might not always conform to human expectations of harmony. Another paradox arises when we step outside the boundaries of Euclidean geometry. The Pythagorean theorem depends on the assumption that space is flat and that the rules of classical geometry hold true. Yet when applied to curved surfaces, such as spheres or the geometry of space-time, the theorem no longer functions in its original form. On a sphere, for example, the sum of the squares of the sides of a right triangle does not equal the square of the hypotenuse. This discovery, made centuries after Pythagoras, challenged the notion that mathematical truths were universal and absolute. Instead, it revealed that the truth of geometry depends on the nature of space itself. The theorem, once considered a fixed law, became part of a larger, more flexible system. What was once seen as eternal began to depend on context, a paradox that blurred the boundary between absolute truth and relative understanding. There is also the philosophical paradox of simplicity and infinity. The theorem's equation is strikingly simple, containing only 3 terms, yet its implications stretch endlessly. It applies to every possible right triangle, from the smallest imaginable to those extending across cosmic distances. It serves as the foundation for vast systems of reasoning, yet it can be written in a single line. This tension between simplicity and infinity mirrors the paradox of human thought itself, that something finite, like a formula, can capture relationships that are boundless. Each proof of the theorem, and there are hundreds known, expresses this paradox anew. Every new proof adds depth to a truth that has already been proven, suggesting that understanding is an ongoing process rather than a single conclusion. Another paradox lies in the theorem's coexistence of abstraction and practicality. It was born from pure geometry, a study of forms existing in thought, but it governs the physical world with precision. Builders use it to square foundations, engineers to design machines, pilots to calculate flight paths, and programmers to create digital landscapes. How can something so abstract, existing entirely in the mind, have such power over the material world? This question reveals a philosophical tension between mathematics as invention and mathematics as discovery. Did Pythagoras create a truth, or did he uncover one that was already written into the fabric of existence? The paradox remains unresolved, resting at the heart of mathematical philosophy, whether numbers are human constructs or the language of the universe itself. There is also a paradox of certainty and mystery within the theorem. It is one of the most proven statements in mathematics, with countless logical demonstrations supporting it. Yet even with such certainty, it continues to inspire questions about why it works so perfectly. Proof explains how, but not why such a simple relationship should describe so many forms of reality. The theorem works not only for physical triangles, but also for abstract concepts like distance in multidimensional spaces. the relationship between energy and momentum in physics, and the geometry of waves in sound and light. Each application expands its meaning, turning a simple geometric rule into a philosophical principle about relationships that govern the universe. The more it is understood, the deeper its mystery seems to grow. The paradox of perception also arises when considering how the theorem unites opposites. The right triangle itself represents contrast, two sides at a rigid right angle, seemingly in conflict, yet brought into harmony by the hypotenuse. In the same way, the theorem unites order and tension, logic and imagination, finite and infinite. It shows that truth can emerge from the balance of opposites rather than from uniformity. This is a profound lesson not only in mathematics, but in philosophy. Harmony does not mean sameness, but equilibrium among differences. Even time has added to the paradoxical nature of the theorem. More than 2,000 years after its conception, it continues to generate new meanings and discoveries. It has survived revolutions in science, shifts in understanding, and transformations in philosophy, yet its core relationship remains untouched. Its endurance challenges the notion of progress, suggesting that certain truths are timeless, existing outside of historical change. At the same time, each new era reinterprets it, finding in it new connections that the ancients could not have imagined. Thus, the paradoxes that surround the Pythagorean theorem make it more than a mathematical statement. They make it a mirror of thought itself. It is a symbol of how clarity and mystery coexist, how reason reveals both order and wonder, and how the simplest relationships can lead to the deepest questions. Beneath its surface of certainty lies an ocean of meaning, where logic meets mystery and the pursuit of truth never fully ends. The influence of Pythagoras' ideas on science and art is vast, profound, and enduring, extending far beyond the bounds of mathematics. His theorem, while often seen as a purely geometric truth, planted the seeds for an entire world, view in which harmony, proportion, and order became guiding principles across disciplines. The belief that numbers could explain the world inspired not only scientific inquiry, but also artistic creation. From the architecture of temples to the rhythm of music and the structure of galaxies, the legacy of Pythagoras can be traced through centuries of human thought and creativity. His theorem did not remain confined to geometry. It evolved into a symbol of balance between intellect and beauty, calculation and imagination, reason and inspiration. In the realm of science, Pythagoras' influence begins with the simple yet powerful idea that natural laws can be expressed mathematically. This notion, radical in its time, became the foundation upon which modern science was built. The Pythagorean theorem demonstrated that numerical relationships could describe physical space with perfect accuracy. This realization opened the door for thinkers like Euclid, Archimedes, and later Galileo to explore nature through mathematical reasoning. Galileo's declaration that the book of nature is written in the language of mathematics is an echo of Pythagoras' philosophy. The theorem that relates the sides of a triangle became the first proof that geometry could uncover the hidden structure of reality, and this concept shaped every branch of physics that followed. The theorem's geometric relationship became a cornerstone for understanding motion, force, and energy. When scientists study vectors in physics, they still rely on the principle that the resultant of two perpendicular forces forms the hypotenuse of a right triangle, a direct application of Pythagoras. Logic. In modern terms, the theorem defines how energy and momentum combine in space, how distances are calculated in relativity, and how trajectories are plotted in astronomy. The Pythagorean relationship lies silently within the equations that describe the behavior of light, the orbits of planets, and even the structure of space, time itself. Einstein's theory of relativity, which unites space and time into a single geometric fabric, is conceptually rooted in the same belief that geometry reveals truth about the universe. Pythagoras' influence also extended into the scientific method itself. His insistence on reasoning, proof, and proportion established the foundation for systematic inquiry. The Greeks were among the first to seek understanding through logical deduction rather than myth, and Pythagoras' approach inspired a new intellectual confidence, the idea that truth could be discovered through mathematics and reason. This tradition carried forward through centuries, shaping the analytical mindset of scientists and philosophers alike. Even in modern research, when scientists reduce complex phenomena to mathematical models, they are following a Pythagorean impulse, the faith that numbers mirror the structure of reality. Beyond science, Pythagoras' ideas shaped the world of art in equally powerful ways. His discovery of the relationship between musical harmony and numerical ratios transformed the understanding of sound and aesthetics. By observing that simple ratios of string lengths produced consonant tones, he revealed that beauty in sound arises from mathematical proportion. This concept influenced not only the development of musical scales, but also the entire philosophy of aesthetics. The belief that beauty is born from order and symmetry became central to classical art, architecture, and design. The golden ratios, the balanced columns of Greek temples, and the perfect symmetry of Renaissance paintings all trace their intellectual roots to Pythagorean principles. In architecture, proportion and harmony became guiding ideals that reflected the mathematical order of the cosmos. The Parthenon in Athens, designed with precise geometric ratios, embodies the Pythagorean spirit of balance between structure and grace. Centuries later, artists like Leonardo da Vinci and architects like Brunelleschi carried this vision forward, blending mathematical proportion with artistic creativity. In Leonardo's Vitruvian Man, the human body is depicted as a system of geometric relationships, demonstrating how nature itself follows mathematical harmony. This fusion of science and art, of measurement and beauty, originates in the same insight that defined the Pythagorean theorem, the realization that relationships define form and that numbers express the essence of creation. Even in music, Pythagoras' influence has never faded. The octave, the fifth, and the fourth intervals fundamental to harmony are all based on the numerical ratios he identified. Centuries later, composers such as Bach and Mozart built their music on mathematical structures, using proportion to create emotional resonance. The rhythm of notes and the architecture of melodies reflect the same principles of balance that govern geometry. Modern sound engineering, acoustics, and digital music production all rely on mathematical ratios that descend from Pythagoras' original experiments with vibrating strings. The concept that harmony can be measured and understood remains a cornerstone of both musical composition and auditory science. Pythagoras' influence also reached the philosophical foundations of art. He taught that beauty was not a matter of ornament but of proportion, that perfection lies in balance rather than extravagance. This idea continues to shape artistic expression, from classical sculpture to modern design. Artists, whether consciously or not, work within frameworks of symmetry, rhythm, and ratio that reflect Pythagorean ideals. Even abstract art, which often rejects visible order, relies on mathematical relationships between color, space, and form. Thus, the dialogue between art and science that began with Pythagoras continues in every creative act that seeks harmony in structure. In the modern age, the legacy of Pythagoras has expanded into new territories. In architecture, his principles guide the design of skyscrapers and urban layouts. In physics, they underpin quantum mechanics and relativity. In computer science, algorithms depend on geometric logic derived from his theorem. The mathematical modeling used in art, animation, and design continues the ancient union of form and number. Even the digital screens through which people view art today rely on pixel grids and distance calculations rooted in the geometry of right triangles. The connection between Pythagoras' insights and modern creativity demonstrates that his ideas are not relics of the past but living forces shaping the present. The influence of Pythagoras on science and art reveals how one idea can transcend its origin and become a universal principle. His theorem taught humanity to see order where chaos seemed to reign, to find beauty in logic, and to recognize that numbers are not lifeless symbols but expressions of harmony. From the construction of cathedrals to the composition of symphonies, from the equations of physics to the pixels of digital art, his vision continues to guide the human pursuit of understanding and creation. The enduring legacy of Pythagoras' theorem and its associated philosophy lies not merely in its mathematical precision, but in its power to connect disciplines, inspire generations, and reveal universal truths that transcend time. It has become more than an equation. It is a symbol of the human quest to understand order, balance, and harmony in the cosmos. The theorem, in its essence, captures a timeless relationship that unites simplicity with profundity, reason with beauty, and logic with wonder. This legacy stretches across centuries, influencing thinkers, scientists, artists, and philosophers who found in it a reflection of both nature's design and the structure of thought itself. The survival and relevance of the theorem, from the ancient world to the age of space exploration and artificial intelligence, stand as a testament to humanity's enduring curiosity and its capacity to uncover patterns hidden within existence. The universality of Pythagoras' theorem lies in its ability to transcend boundaries of culture, time, and language. In ancient Babylon and India, similar relationships between the sides of right triangles were known, but it was through Pythagoras that the relationship became a principle, a universal truth proven by reason. This universality made the theorem a cornerstone of mathematics, serving as a common language through which civilizations could communicate ideas of structure and proportion. Whether drawn on parchment, carved in stone, or simulated on digital screens, the relationship expressed in the theorem remains unchanged. Its constancy mirrors the stability of natural laws, the predictability of motion, and the order that underlies chaos. It is not bound to a culture or an age. It belongs to all who seek understanding through logic. Through time, the Pythagorean theorem has woven itself into the evolution of human knowledge. In the Middle Ages, it was studied by Islamic scholars who expanded upon its geometric principles, linking it with algebra and trigonometry. Later, during the Renaissance, European thinkers rediscovered it, using it to merge art and science into a single language of proportion and balance. It became a bridge between disciplines, a reminder that mathematics was not isolated from philosophy, music, or design, but intimately connected to them. As scientific revolutions unfolded, the theorem continued to evolve, not in form, for its truth remained constant, but in meaning. It came to symbolize the human capacity to uncover the invisible architecture of reality, to perceive unity beneath apparent diversity. In modern times, the theorem's influence extends into every realm of scientific and technological advancement. In physics, it defines the structure of forces and motion. In engineering, it underlies every calculation of stability, from bridges to spacecraft. In computer science, it governs the algorithms that determine distances, angles, and coordinates in digital space. Even in data analysis, the concept of distance, whether between points, datasets, or vectors, owes its foundation to Pythagorean reasoning. In this sense, the theorem forms part of the invisible framework of the modern world, shaping systems, structures, and technologies that sustain civilization. Its simplicity allows it to adapt endlessly, proving that eternal truths are not static but capable of infinite expression. Beyond the scientific realm, the theorem continues to carry philosophical weight. It embodies the idea that truth can be expressed through simplicity, that complexity can be understood through relationships, and that beauty arises from balance. Pythagoras' belief that the universe is structured according to number resonates today in the search for mathematical models that describe everything from atomic behavior to cosmic expansion. The theorem, by showing the perfect relationship between three sides of a triangle, represents the broader principle that nature itself operates through proportion. It whispers of a cosmos governed by logic, yet filled with mystery, reminding humanity that knowledge is both a discovery and an act of wonder. The theorem's endurance also reveals something profound about human nature, the desire for permanence in a transient world. Empires rise and fall, languages evolve, and beliefs transform, but the relationship expressed by a 2 plus b 2 equals C2 remains untouched. It is a truth that does not decay with time, unaffected by human interpretation or cultural change. This permanence gives it an almost spiritual quality, suggesting that some aspects of reality exist independently of perception. Philosophers have long pondered whether mathematics is invented or discovered, and the theorem stands at the heart of this question. Its existence before human awareness seems plausible, as if it were waiting to be found, a hidden law embedded within the structure of space itself. The theorem's legacy also lives in education, where it continues to serve as a student's first encounter with the power of proof. For centuries, young minds have experienced the moment of revelation when they realize that reason can create certainty. That moment is not just mathematical, it is transformative. It marks the awakening of logical thought, the realization that the world can be understood through reasoning rather than belief. Each generation that rediscovers the theorem participates in a lineage of thinkers stretching back to antiquity, contributing to a continuous dialogue between past and future. The theorem thus becomes not merely a lesson, but a rite of passage into rational inquiry. In art and culture, the theorem's influence can be felt in the very idea of symmetry and balance. It inspired artists to see geometry as beauty and architects to construct with precision. Even modern design, from digital interfaces to urban planning, relies on proportions that reflect Pythagorean harmony. The theorem's geometric clarity symbolizes intellectual elegance, showing that form and function can coexist in perfect proportion. It stands as a metaphor for harmony within difference, each side of the triangle distinct, yet united in an eternal relationship of equality and purpose. The enduring power of the Pythagorean theorem lies in its duality. It is both a scientific formula and a symbol of philosophical truth. It speaks to the measurable and the immeasurable, the concrete and the abstract. Its timelessness lies not only in its ability to solve problems, but in its invitation to reflect on the nature of truth itself. It shows that beneath every structure, whether physical, intellectual, or moral, there exists a geometry of relationships that defines balance. This insight extends beyond mathematics into life itself, teaching that harmony is not an accident but a consequence of proportion, that understanding is not the end of curiosity but its continuation, and that in every equation lies a reflection of the universe's eternal design.